Diamond is a solid form of the element carbon with its atoms arranged in a crystal structure called diamond cubic, at room temperature and pressure. Another solid form of carbon known as graphite is the chemically stable form of carbon. But diamond almost never converts to it. Diamond has the highest hardness and thermal conductivity of any natural material, properties that are utilized in major industrial applications such as cutting and polishing tools. They are also the reason that diamond anvil cells can subject materials to pressures found deep in the earth. Because the arrangement of atoms in diamond is extremely rigid, few types of impurity can contaminate it. Yellow, purple, pink, orange, or red. Diamond also has relatively high optical dispersion. Most natural diamonds have ages between 1 billion and 3.5 billion years. Most were formed at depths between 150 and 250 kilometers. They were carried to the surface in volcanic eruptions and deposited in igneous rocks known as kimberlites and lamproids. Synthetic diamonds can be grown from high-purity carbon under high pressures and temperatures or from hydrocarbon gas by chemical vapor deposition. Imitation diamonds can also be made out of materials such as cubic zirconia and silicon carbide. Natural, synthetic and imitation diamonds are most commonly distinguished using optical techniques or thermal conductivity measurements. Diamond is a solid form of pure carbon with its atoms arranged in a crystal. Solid carbon comes in different forms known as allotropes depending on the type of chemical bond. The two most common allotropes of pure carbon are diamond and graphite. In graphite the bonds are sp2 orbital hybrids and the atoms form in planes with each bound to 3 nearest neighbors 120 degrees apart. In diamond they are sp3 and the atoms form tetrahedra with each bound to 4 nearest neighbors. Tetrahedra are rigid, the bonds are strong, and of all known substances diamond has the greatest number of atoms per unit volume, which is why it is both the hardest and the least compressible. It also has a high density, ranging from 3,150 to 3,530 kilograms per cubic meter in natural diamonds and 3,520 kilograms per cubic meter in pure diamond. In graphite, the bonds between nearest neighbors are even stronger but the bonds between planes are weak, so the planes easily slip past each other. Thus, graphite is much softer than diamond. However, the stronger bonds make graphite less flammable. Diamonds have been adapted for many uses because of the material's exceptional physical characteristics. Of all known substances, it is the hardest and least compressible. It has the highest thermal conductivity and the highest sound velocity. It has low adhesion and friction, and its coefficient of thermal expansion is extremely low. Its optical transparency extends from the far infrared to the deep ultraviolet and it has high optical dispersion. It also has high electrical resistance. It is chemically inert, not reacting with most corrosive substances, and has excellent biological compatibility. The equilibrium pressure and temperature conditions for a transition between graphite and diamond are well established theoretically and experimentally. The pressure changes linearly between 1.7 gigapascals at 0 K and 12 gigapascals at 5000 K. However, the phases have a wide region about this line where they can coexist at normal temperature and pressure, 20 degrees Celsius in one standard atmosphere. The stable phase of carbon is graphite, but diamond is metastable and its rate of conversion to graphite is negligible. However, at temperatures above about 4500 K, diamond rapidly converts to graphite. Rapid conversion of graphite to diamond requires pressures well above the equilibrium line. At 2000 K, a pressure of 35 gigapascals is needed. Above the triple point, the melting point of diamond increases slowly with increasing pressure, but at pressures of hundreds of GPa, it decreases. At high pressures, silicon and germanium have a BCC body-centered cubic crystal structure, and a similar structure is predicted for carbon at high pressures. At 0 K, the transition is predicted to occur at 1100 gigapascals. Research results published in an article in the scientific journal Nature in 2010 suggest that at ultra-high pressures and temperatures diamond behaves as a metallic fluid. The extreme conditions required for this to occur are present in the gas giants Neptune and Uranus. Both planets are made up of approximately 10% carbon and could hypothetically contain oceans of liquid carbon. Since large quantities of metallic fluid can affect the magnetic field, this could serve as an explanation as to why the geographic and magnetic poles of the two planets are unaligned. The most common crystal structure of diamond is called diamond cubic. It is formed of unit cells stacked together. Although there are 18 atoms in the figure, each corner atom is shared by 8 unit cells and each atom in the center of a face is shared by 2. So there are